This video, we're going to talk about finding relative extrema. So we're going to find critical numbers and use the first derivative test that we were using last time to talk about increasing and decreasing functions to identify relative extrema. We also have a second derivative test for extrema, and we will talk about how to use that as well. So let's go ahead and get started here. We go ahead and start with number one. I'll show you both the first derivative test and the second derivative test for this. The first derivative test is going to look very familiar because you have basically already done that in the last section. So we've got our domain here of negative infinity to infinity, since this is a polynomial. When we find our critical numbers here, we have negative 4x plus 4 is equal to 0. I would factor out that negative 4 to make a factor of x minus 1 that would be equal to 0, and x would be equal to 1 as our critical number. And then we're going to, I'll show you with the first derivative test here first. Put your critical number here at 1. That makes an interval of negative infinity to 1, and an interval of 1 to infinity to test. Pick a number less than 1, like 0. Negative 4 times a negative 1 is a positive 4, and that means that we're increasing. And then to the right of 1, like 2, 2 minus 1 is 1. 1 times negative 4 is a negative 4, which means that we're decreasing on this interval. We go up and then come back down. There's a local max at x equals 1. If we go ahead and stick that x value in to our original, we have negative 2 times 1 squared plus 4 times 1 plus 3 is negative 2 plus 4 plus 3. 7 minus 2 is 5. So there is a relative or local maximum of the y value 5 at x equals 1, but we really shorthand that most of the time and just say there's a relative or local max, and then we'll give the x coordinate and the y coordinate. Really, the maximum or minimum is the y value, and it happens at the x value. I just want you to be aware that this is kind of a shorthand to say all these words here when we just give the ordered pair like that, but really we're talking about a minimum or maximum y value that happens at an x value. Let's go ahead and talk about what happens if we find the second derivative here and how that could help us to establish whether we have a minimum or a maximum here. So we've talked about higher order derivatives. Our second derivative is negative 4, and that happens across the entire real number line, that the second derivative is negative, meaning that we are what's called concave down. We'll talk a lot more about concavity later, but concave down means that it has this kind of a shape to it where it's opening down. If it's opening down and there's a critical number in that concave down piece, that critical number has to represent a local maximum. So if f prime of c is equal to 0 and f double prime of c is less than 0, f of c is a local max. If f prime of c is equal to 0 and f double prime of c is greater than 0, f of c is a local min. If f of f prime of c equals 0 and f double prime of c equals 0, the second derivative test fails. Use the first derivative test. Okay, so and we'll talk more about what that is when the second derivative equals 0. That's another special kind of point later that we'll talk about coming up in this chapter. Let's move on to number 7. Number 7 says h of x is equal to negative x plus 4 to the third. So my first derivative, h prime of x is equal to a negative 3 x plus 4 squared. And that's going to have a critical number of x equals negative 4. And my second derivative will be negative 6 x plus 4. And I see that it also has a 0 at negative 4. So that's not gonna work. If I take this and plug it in, that's 0. So second derivative test fails. Let's go back to the first derivative test here and see what happens at my critical number negative 4. To the left of negative 4, I have a negative squared as a positive times a negative as a negative, and I'm decreasing. To the right of negative 4, I have a positive squared as a positive times a negative as a negative, and I'm decreasing. Since there's no sign change, I'm decreasing, and I continue decreasing. This is something that's like so. Then I have no local extrema. And that's that. Move on to number 9. Nine says f of x is equal to 5x cubed minus 10x squared plus 3. F prime of x is equal to 15x squared minus 20x. I factor out 5x. I get The remaining factor is 3x minus 4, giving me critical numbers of x equals 0 and 4/3. So f double prime of x is equal to 30x minus 20. F double prime of 0 is equal to 0 minus 20 is a negative 20. So there's a local max at x equals 0. F double prime of 4/3 is 30 times 4/3 minus 20 is 40 minus 20 is 20. So there's a local min at x equals 4/3. We could also have done that with the first derivative test. I'll need to figure out what those values are here in just a second, but if you preferred the first derivative test, we could have put 0 and 4/3 on the number line, and we would have a number less than 0 when we plug it into our first derivative. Would have been a negative times a negative as a positive would be increasing. A number between 0 and 4/3, like 1, would give me a positive times a negative as a negative, which would be decreasing. A number bigger than 4/3, like 2, would be a positive times a positive, would be increasing. And so when I go from increasing to decreasing, there's a local max. When I go from decreasing to increasing, there's a local min. So let's go ahead and stick those numbers back into my original. F of 0 is equal to 0, minus 0 plus 3 is 3, and f of 4/3 is equal to 5 times 4/3 cubed minus 10 times 4/3 squared plus 3. Now, I really don't want to do it that way. I'm going to use synthetic division to help me because I don't like cubing and squaring a whole bunch of fractions. So negative 10, 0 for the coefficient on x, 3. So this is going to be 20/3, 30/3. Negative 30/3 plus 20/3 is negative 10/3. Then that's negative 40/9. And then that is negative 160 over 27. So negative 160 plus 81 is negative 79 over 27. Let's see if we get the same thing this way. 5 times, that's 64 over 27 minus 10 times 16 over 9, which I need to multiply by 3 over 3 to get to a denominator of 27, plus 3 over 1 times 27 over 27 will be 320 minus 480 plus 81 over 27. So that's 401 minus 480. So that is 79, but in the negative direction, negative 79 over 27. So that was a local max of 0, 3, and a local min of 4/3 negative 79/27. Okay. Let's look at number 11 now. Number 11 says f of x is equal to 6x to the 2/3 plus 4x. We've only talked about minimums or maximums that were smooth curves that look like this so far, or this. Now we're going to have one that makes a node or a cusp of some kind, like this, or like this, or like that, something where it comes to a sharp point because of this even over odd exponent. It's going to make a cusp like that. Absolute values would make a node. Our domain is still all real numbers here. Our derivative is going to be 12/3 is 4 x to the negative 1/3 plus 4 is going to be x to the 1/3 multiplied by x to the 1/3 over x to the 1/3 is 4 plus 4x to the 1/3. It's 4 times x to the 1/3 plus 1 over x to the 1/3. So I have critical numbers of x is equal to -1 and x is equal to 0. So when that happens, let's go ahead and just use the first derivative test here. I don't really care for the second derivative test where I'd have to use the quotient rule here. -1 and 0. When I stick in a number less than -1, then I get a, let's stick in, for instance, a -8. Then I get a -2 plus 1 is a -1 times a 4 is going to be a -4 over a -2. So that's going to be positive, and that makes this increasing here. Between -1 and 0, let's go for -1/8. That's going to be -1/2 plus 1 is +1/2 times 4 is a +2 over a -1/2. That's going to be a -4. So 2 over a -1/2 will be a -4. So that's decreasing. Let's go for 1 here to the right of 0. 1 plus 1 is 2 times 4 is 8 divided by 1 is a +8. Makes this increasing. And so increasing to decreasing is going to be a local max. Decreasing to increasing will be a local min. Local max. So f of -1 is 6 times 1 plus 4 times -1 is 6 minus 4 is 2. There's a local max at -1, 2. F of 0 is 6 times 0 plus 4 times 0 is 0 plus 0 is 0. So there's a local min at 0, 0. just take a look here. See if I have any more like that where I'm doing relative extrema. No. So we'll come back in the next video and we'll add another layer to this where we want to talk about absolute extrema on a closed interval. And those absolute extrema can happen at these relative extreme values in the middle of the graph, or they can happen at the endpoints on the end of the graph, that the endpoints could be higher or lower than my points in the middle of the graph, and I need to test those as well. That's called absolute extrema on a closed interval. So we'll come back and test for those next time, again using the first derivative test or second derivative test to find my local extrema. Really just need my critical numbers though, and I can find out what is my highest y value and what is my lowest y value. It either has to happen at a critical number or it has to happen at an endpoint. So I don't need to do as much of the test, but I do have a couple extra numbers that I have to evaluate in the original function. So we'll work on that next time when we come back. See you for the next video.